Okay, now let me finish the characteristic and summarize what's the difference from other, and then I'm going to look for real cases to see where you could fall down to the pit and get nonsense. And first, that is the only thing you learn that's called instance-based learning. What's instance? Instance means you only learn from example. There's no theory here. We did not bring any theory, say like a decision tree, Bayesian, or something. You know, those are model-based. Those are model-based. Once the model is built, take a long time to build the model. Once the model is built, you don't need the instance anymore. You just throw it away and fit it into the model. Whatever result comes from the model, right? You build the machine first. The machine take care of the rest. But here, there's no model, no machine. All you have is the instance. So when it comes, you just start to check the distance. If they're close, and then you vote, you get the result. If you want to write the program yourself in C, Java, whatever, 10 lines, 20 lines, good enough. You can write, anybody can write. So the training time is very short, but the processing time is going to be long, because each time when a new case comes, you need to calculate all the distance, to all the training instance you have. That will be, the processing should be long. If you have a huge number of things you want to test, that's not a good choice. Unless you're numbered, or in another way, if it's a dynamic case, you have an instant case, all come year after year after year, that's not a good choice. If all you have is this many examples, then you need to test, that's the quickest one, because you're done, right? So it's good for your static case. After you finish this, no more like our galaxy. We wanted to classify it, and you don't come like a new galaxy every year. You just have this many. You're done. So the training time is short, but the testing time is very long. You have to test all the way. The distance measure is your definition, and you need a classified function. The classified function is nothing more than the vote function. You just say, hey, now I've got all the distance, my top 5 is out, and then look at the top 5, which class it is, then the majority vote. Or use the reverse distance, give some weight. So the choice of k is a trade-off of the sensitivity. Small k is very sensitive to the particular case. And it's not so noise-proof. It could be very easily overfit. But the big K, you're going to get the other complication. Mostly, it's harder to set the boundary, because sometimes you add a little bigger, they change the class. And you don't know what's the outer circle.
Too many opinions.
Yeah, too many dependents, yes. Too many opinions, you're right. So the committee needs to always be a decent size when you really want to make a serious decision. Okay, so come back to democracy and republic. That's the subtle issue. Republic means we are going to control the size each time the opinions to say that democracy just stop all the way from the bottom to the top. So it depends. Democracy has more stability, but harder to correct. So instant-based, that's all you have. You always keep that in your record, just like the poor student just remembered a few examples. When it comes to the test, they always wish that's one of the examples they remembered. That don't need a lot of understanding. They said, oh yeah, that's what I saw before in the homework. That's one way to do it. That's called the rote type of learning. The rote learning is a lazy learn. They learn only what they need, and then remember that the example, try to match the example. Basically, that's what you do. It's based on the memory matching, and in the book I talked about the people so quick thinking like that. They don't really get into model, get into depth. All they think is a stereotype with fit. That's the decision. And they did another trick at the deep learning. Deep thinking, that's the slow thinking. But no mistake, this method is the most frequently used method. It's very powerful too. In classification, you're going to see it again. Even you don't have any class label, don't have supervised learning, you don't have anything, they can help you based on so-called physical science concept of centroid. And you in each galaxy, you look at the centroid, the center, and look at each cluster have the average short distance, and you cluster them together. And this can be very useful for the unsupervised learning. You know, like how do we define all those galaxies? It's based on this centroid method that we just give a type. That's how. The power is very strong. So after we call it the eager learner. The eager learner like decision tree and the basic method and what we're going to learn. They have a model, they learn everything well, and then whenever come and just run past quickly. You know, learn very slower, but once they learn the model, they can easily pass, right? If you get a huge case, dynamic keep going, you do not want that. So here, in the nearest neighborhood, classify on non-record is relatively expensive because you have to calculate the distance again to everything. Okay, now let's look at some alternatives. Distance. One is called parallel example. Before I come to here, let me ask the prospect. Hello, Sean and Alex. Have any questions so far?
No, we're good.
Now you're good? All right, let's go to a few examples. This is the real meat of what's good and what's bad. And you're going to see. For that example, we call it parallel example-based learning system. To look at the cost, we choose the k equal 1. We just found the nearest one, basically, to match it. We can, for each record, we assign a weight factor. Look at the weight factor. First, we define the distance. They can work for both the nominal or numerical attributes in the same way. Or you can call this as L1 distance if you are good in math. Just means there's no square root. Square root, we call it L2. That's L1. Look at the absolute value. Now we compare, in this case, we used a lot of times, compare the marriage status, how they are classified, use single, married, and the divorce. Those are the three values of this single attribute. And then you look at single, they have 4 cases of a single. Each one is 2 out of 4, right? And the evil case, just like the entropy. 2 out of 4, and the one is married, you see 0 out of 4. It's all unanimous, no, you see? And then this is 2 out of 4 minus 0 out of 4. This is the number for one class over the total number minus the other instance with the same class over the total instance. So 2 out of 4 is from the single, 0 out of 4 is from the married, that's for that married status. And then the other class, 2 out of 4, that's no class, 2 out of 4, and the 4 out of 4 from the no class. And then the distance is 1. And intuitively thinking, married give you a 0 entropy. Can you see it? It's all 4. And this get you the highest entropy. Half and half, right? That means no information here. So if that distance is 1, when you compare single and the divorce, the distance of these two are also have no information, half and half. Can you see? The distance is 0. 2 out of 4 minus 1 half, that's for the yes class. 2 out of 4 minus 1 half from the no class, there's no distance. The no both have no information basically. From the married to divorce, the distance is 1. You can see married and the divorce, one is 0 entropy, this is full entropy, the same as this, is 1. But look at the money found. Refund equal yes, refund equal no, you can see that difference. The yes class is 0 out of 3, and the no class is 3 out of 7, that's this distance. And then, so the same as no is 6 out of 7. Now, the total distance, when you add that, that's just the distance from the attributes. And that's uniform way you look at the distance if the weight are all the same. But you don't have to weight the same. The total distance of the two cases, you can put that weight here. The weight is the credibility. So now the distance is what you see. You can change another distance here. You can use Euclidean distance, square, but not square root. That is the number of x used for prediction divided the number of time predicted correctly. So if this number, each time you always predict it right, then this number is 1, right? If this will always be 1, that means reduce the distance. Are you with me? That will give more credit, because a small distance means I have more credential, right? Big distance means your voice have little weight. So if I always do it right, I got more weight. But on the other hand, if this the time of prediction is 100, I only got 1 time right. That is 100. That will give a huge distance. Are you with me? You just look at the two extremes. A huge distance means your opinion does not count, right? So we give more weight to the people with more credential. That's a meaningful way, right? So it all depends on this case.